students, welcome to Sunil's tutorial. I'm Sunil Menwani and today we'll be doing this chapter called as thermodynamics. Now, last lecture we were learning about spontaneity. Question: why do you need to know the spontaneity of a reaction? Right? How does spontaneity help in a chemical reaction? Let's try to find out the relationship between energy and spontaneity. Let's try to find out the relationship between energy and spontaneity. Now, the stability of a substance is related to its energy. How stable a substance will depend upon how much energy the substance possesses. Stability of a substance. Excuse me. So, stability of a substance depends upon substance is related to energy. Right? Stability of a substance is related to energy. The less energetic a substance is, the more stable it will be. Higher the energy possessed by a substance, less is the stability of the substance. So if you want a substance which is more stable, the lower the energy the substance possesses, the more is the stability. That is the relationship between stability and energy. They are inversely proportional to each other. The lower the stability, the higher will be the energy, and vice versa. Right? So I can say that less energetic species are more stable. Right? So now comes the actual use of a spontaneous reaction. What did we say a spontaneous reaction is? A spontaneous reaction is the one in which substance with more energy is converted into a substance of lower energy. Or in short, I could say that the reaction proceeds in the direction where the energy of the system decreases. Right? So in spontaneous reaction, substances with more energy, are converted to substances with low energy. Converted to substances with low energy. That's what happens in a spontaneous reaction. Thus, for a chemical reaction to occur spontaneously, it should liberate heat, because substances of higher energy, if they are getting converted into substances of lower energy, that means the substance is liberating heat. So I can say thus, for a chemical reaction to occur spontaneously, it must liberate heat. Right? Now, that means is it true that all spontaneous reactions liberate heat and all of them are exothermic? Not necessarily again. Right? So I can say, however, for spontaneity of a process, exothermicity is not sufficient criteria. because because there are spontaneous reactions which may not be exothermic. As I told you that it's not only that a reaction should be exothermic for it to be spontaneous. An endothermic reaction could also be spontaneous. I'll give you an example. Just let me finish writing this. Exothermicity is not a sufficient criteria because there are spontaneous processes. There are spontaneous processes that are endothermic. Right? For example, if you want me to give you an example of an endothermic spontaneous reaction, very simple example. If I take ice at 0 degrees Celsius, or no, if I take ice above 0 degrees Celsius, it will immediately get converted into water. Now, if ice is getting converted into water, that means heat energy must be absorbed. That means this is definitely an endothermic reaction, and if the reaction is occurring above 0 degrees centigrade, that means the reaction will occur very fast. It is going to be a spontaneous reaction, and it is also going to be an endothermic reaction, right? So that is what we were talking about. You will get water, right? Say the amount of heat energy that will be absorbed here is plus 6 kilojoules per mole. So thus we said that it is just not exothermicity which is the essence of spontaneity, right? So energy is not the only criteria for spontaneity of a reaction. There must be some other criteria also. Thus, energy is not the only criteria for spontaneity. There must be some other factor also. So here we know that stability depends upon energy, energy depends upon spontaneity, right? But spontaneity does not depend, energy is not the only criteria that determines the spontaneity of a reaction. There has to be some other criteria also. Let's try it. So that's my relationship between energy and spontaneity, right? Now let's try to learn a new concept now. We have seen enthalpy. Let's try to understand entropy. Right, what do we understand by entropy? Right, let's try to understand this. The spontaneity of a process is determined by some thermodynamic property. Let's call that as entropy. Right, we said that energy is not the only criteria that will determine whether a reaction is spontaneous or no. Because if exothermic and endothermic both reactions can be spontaneous, that means energy is not the only criteria. There has to be something else. Let us assume that there is some other thermodynamic property called as entropy, right? And then let's try to understand what is entropy, right? The spontaneity, we are trying to find out what is that other criteria that determines whether a reaction will be spontaneous or no. The spontaneity of the process is determined by a thermodynamic property called entropy. Right? What exactly is entropy? Guys, let's try to understand. Let's consider the example that we had taken above. Let's take ice. This is ice, right? Ice is in ordered state. If you consider ice, it has a highly ordered arrangement of water molecule, it has a highly ordered arrangement. The molecules are closely packed. They have certain motion that they can perform, right? Let's assume that when I heat ice, let's consider melting of ice. If I consider melting of ice, I will get water, where the water molecules will be slightly far away from each other. Right? Here you have water which is a disordered state. This was a definitive shape. This is not a definitive shape, right? This is water which is disordered state, right? If I further heat this, you will have vaporization of liquid taking place. Vaporization of liquid, right? In which case I will get gas molecules which will be in random motion, right? This is gaseous water. This is highly disordered state. So as I heat the substance, its disorderliness goes on increasing. What we see here is, as I go on heating a substance, its disorderliness goes on increasing, right? So in melting of the ice, the highly ordered arrangement of water molecules in ice breaks down into a disorderly arrangement or disordered state, and the molecules then are free to move. In ice, the molecules are not free to move. In melting ice and vaporization of liquid, disorderliness or randomness of the molecule further increases. This degree of molecular disorderliness or randomness is called as a thermodynamic property, which is entropy. So what is entropy? It is the degree of disorderliness that is present in a molecule. If it is, or do you understand what is entropy? Entropy is a property that indicates the extent to which a substance is going to be in disorderly state. Do you understand this? So I can say that, for example, anyway, that's not the definition of entropy. I'm trying to first explain the concept of entropy, then I'll give you the definition. For example, in melting of ice, highly ordered arrangement of water molecules. In ice breaks into disordered state. Right? And the molecules move freely. In liquid state. Now further, if I heat it from liquid state, in melting of ice and vaporization, of liquid water. In vaporization of liquid water, disorder or randomness of the molecule increases. Disorder of molecules increases. Right? We can see that from the figure. So So the degree of molecular disorderness is measured by a thermodynamic property which is called as entropy. You understand what is entropy? So I can say that the degree of molecular disorderness, the degree of molecular disorderness is measured by a thermodynamic property called entropy. Right, do you get this in here? So do you understand what is entropy? Now, so in entropy, what are we going to try to find out? We are going to find out what is the degree of disorderliness. Fine, do you get this in here? Next, let's move on ahead. If that is entropy, what do we understand by entropy change? Right? Now, when you have a solid substance, substances are in highly ordered states. Hence, the smallest entropy. On the other hand, if you see gaseous substances are in highly disordered state and have the highest entropy. That means I can say that the entropy of the substance increases from solid to liquid to gaseous state because the degree of randomness increases. Obviously, therefore, the entropy should increase. Therefore, I could say that in melting ice and in vaporization of liquid, entropy change is going to be positive. If the degree of randomness increases, entropy increases, that means entropy is going to be positive, right? Do we understand this? So thus I could say that entropy measures the extent of molecular disorderness. So entropy increases as the disorderliness increases, right? Okay, let's write this much down. In solid substances, all the solid substances are of highly ordered state. Solid substances are of highly ordered state. Hence, smallest entropy. Hence, have smallest entropy. Right? On the other hand, gaseous substances. Are in highly disordered state. Hence highest entropy. Right? From this explanation, you can definitely say that entropy of the substance increases from solid to liquid to gaseous state. From solid to liquid to gaseous state. Right? Thus, in melting ice and in vaporization of liquid, if we say that the entropy is increasing, now remember it is increasing, thus in melting ice and vaporization of liquid, entropy must be positive. The change in positive. How do I know that the change in entropy is positive? Because we just stated that entropy is going to increase, right? So on the basis of this, how do I define entropy change? Definition, right? Now it is very difficult to measure to what extent a substance is in disorderly state or in random state. Hence, entropy change of the substance is defined as entropy change of a system in a process is equal to the amount of heat transferred to it in a reversible manner divided by the temperature at which the transfer takes place. Divided by the temperature at which transfer takes place. Guys, if I'm converting ice to water, I'm supplying heat. If I'm converting water to vapor, I'm supplying heat. That means entropy has to be related to heat. Now it is not necessary that ice will be at 0 degrees. You may be changing ice to water at room temperature, you may be changing it at 10 degrees. Hence, at different temperature, different amount of heat would have to be supplied to it, because the spontaneity of the process would change. If I'm going to melt ice to water at room temperature, it will melt faster than if I try to melt it say at 10 degrees. So that means the amount of heat that would be required to convert it at room temperature will be less than the amount of heat that I would require at 10 degrees centigrade. Therefore, we say that the amount of heat divided by the temperature at which the transfer is taking place. That is what is entropy. So mathematically, or in terms of definition, this is how we calculate. In terms of concept, what is entropy? Entropy is the degree of randomness. But degree of randomness not possible to measure. So in order to have it in some method where I can quantify it, this is the method in which I can quantify it and I can measure it. It is the amount of heat that is given to a matter divided by the temperature at which it is given to it. Right? Thus, I can say that change in entropy delta S, entropy is represented as S, is reversible heat divided by temperature. Right? If this is change in entropy, then what will be the units? The units of change in entropy. Heat. Heat we know is nothing but joules. Temperature is nothing but Kelvin. So joules per Kelvin. The units of entropy are joules per Kelvin. Right? Now, let's talk more about change in entropy. Now, I have ice, I have converted it into water. I can convert it into water at 10 degrees, 15 degrees, 20 degrees. I will have some amount of ice and I will have some amount of water, irrespective of the temperature at which I convert it. I will have the same quantity of ice and I will have the same quantity of water. That means I can say that entropy is a state function, because it depends only upon the initial and the final state and does not depend upon the path taken to change from the initial state to final state. Otherwise, then I would have had different quantities. If it depended on path, if I would have changed the path from 10 degree to 15 degree to 20 degree, the path would have changed. As the temperature would have changed, the path would have changed and I would have got different quantity. But that does not occur. Right? So therefore, I can say that entropy is a state function. Is a state function. Entropy is a state function, as change of entropy depends on initial and final states. Change in entropy depends upon initial and final state, and the path connecting these states. Right? So we know now in that case that entropy is a state function. Now, when heat is supplied to a system, what else would happen to a system? The kinetic energy of the system would increase. If I want to supply heat to a system, the kinetic energy of the system would increase, and hence the molecular motion would increase, and that is the reason why the entropy would increase, because if the molecule motion increases, the degree of randomness would increase. If you think about it, guys, in solid there is very little molecular motion. As you move from solids to liquid, the molecular motion further increases. From liquids to gases, the molecular motion further increases. Gas molecules are in constant random motion, right? So therefore I could say that entropy is directly proportional to the heat energy supplied. More the heat energy supplied, more will be the kinetic energy of the molecule, and more will be the molecular motion of the molecule. So therefore I can say that entropy is directly proportional to the heat supplied. How? When heat is supplied to a system, when heat is supplied to a system, it increases the kinetic energy of the molecules. It increases the kinetic energy of molecules, right? And hence the molecular motion. Molecular motion. It increases the kinetic energy of the molecule and the molecular motion. Thus, as the molecular motion increases, the degree of randomness would increase. Thus, I can say entropy increases. Therefore, I can say that change in entropy is directly proportional to the heat supply. That's another property of entropy, right? Now, the effectiveness of addition of heat increases the molecular motion. Also depends upon the temperature at which the heat is supplied. To what extent will the kinetic energy increase and the molecular motion increase will depend upon the temperature at which heat is being supplied, right? Because if it is already in disorderly state, if I supply heat, it would not go in more disorderly state, right? That means a system which is at high temperature has high disorder or randomness, right? If I add certain amount of heat to the system at a lower temperature, that would result in considerable increase in disorder. As the system has small disorder, at a high temperature the degree of disorderness would be less, whereas at lower temperature the degree of disorderness would be higher, and that is the reason why, if you see the definition, I'm now going to prove it to you why I need these two factors in my definition. The degree of disorderliness depends upon the heat energy supplied. I explained to you how. The degree of disorderliness will also depend upon the temperature at which the heat energy is supplied. If heat is supplied at a higher temperature, the disorderliness will not increase. But if heat is supplied at lower temperature, there will be a greater change in the disorderliness, and that is the reason why the definition says that the heat supplied at a given temperature, right? Do we get this in here? I can say that the effectiveness, I'm here proving it to you why entropy can be mathematically measured that way. The effectiveness of the addition of heat, the effectiveness of the addition of heat to increase the molecular disorder to increase the molecular disorder depends upon the temperature. Also depends upon temperature as temperature takes into account temperature takes into account the disorder already present in the system. Disorder already present in the system. That means if a system is at high temperature, it is already at high disorderly state. Supplying heat would not change the disorderliness. But if a system is at low temperature and if I supply heat to it, then even a small application of heat would bring about a large change in the disorderliness and hence a large change in entropy. Right? This implies that change in entropy is inversely proportional to temperature. If it is at low temperature, there will be a greater change in entropy. If it is at high temperature, there will be less change in entropy. So thus these were the two factors with the help of which I could measure entropy. Right? Next, let's see entropy and second law of thermodynamics. Now guys, we have already seen the second law of thermodynamics. Let us see how entropy affects the second law of thermodynamics. The second law of thermodynamics says that the flow of heat is always unidirectional. The flow of heat is always unidirectional and it is always from a higher temperature to a lower temperature. That is second law of thermodynamics. Let's try to find out the relationship between entropy and second law of thermodynamics. Suppose if I am melting ice at a temperature which is above 0 degrees centigrade and vaporization of liquid, let's assume that I do vaporization of liquid at a temperature above 100 degrees centigrade, then the process will definitely be a spontaneous process, right? Now, if it is a spontaneous process, there would be a change in entropy because heat energy is going to be absorbed by the system, but there are spontaneous processes in which entropy can also decrease. For example, first let me show you how the entropy increases. Suppose melting of ice above 0 degrees centigrade and vaporization above 100 degrees Celsius are spontaneous processes. Right? For these reactions, the entropy increases due to the increase in the disorderliness. For these reactions, entropy increases due to the increase in disorderness, right? Thus, I can say that in a spontaneous process, entropy increases. Thus, in a spontaneous process, entropy increases, but there are spontaneous processes in which the entropy decreases. But there are spontaneous processes where entropy decreases. Let's see those processes where entropy decreases. There are processes where the entropy decreases, right? For example, if I have hydrogen, example, suppose if I have hydrogen gas reacting with oxygen gas to give you water, amazing reaction. Water liquid. Now, as you can see that they are changing from gaseous state to liquid state. If a substance is going to change from gaseous state to liquid state, that means the degree of randomness would decrease. If the degree of randomness is going to decrease, that means entropy is going to decrease, right? So there are, and this is a spontaneous process. When you have hydrogen reacting with oxygen, you would have water molecule formed. The change in entropy here is minus 327 joules per Kelvin. So thus you can have spontaneous processes where the entropy decreases, thus the randomness of the system decreases though it is spontaneous. That's my example of it. Now, how does this occur? This reaction is explained to us by thermodynamic second law, right? I can say thus, you can have randomness of the system decreases. Randomness of the system decreases though it is spontaneous. Right? This is explained. The above example can be explained using second law of thermodynamics. The above example can be explained by using second law of thermodynamics. Right? How? The total entropy of the system and its surrounding increases in a spontaneous process. Second law of thermodynamics says that the flow of heat is unidirectional, which means that the total entropy of the system and its surrounding, increases in a spontaneous process. That is what my thermodynamic second law states. That means I can say that the total entropy of a system is equal to total entropy of the universe is the entropy of the system and the surrounding entropy of the surrounding. Right? Now, we know for sure that the change in entropy of the universe, total means universe. It already said what is universe and system. The part which is not under thermodynamic consideration is called as universe. So the total entropy change of the universe is equal to total entropy of the system plus the total entropy of the surrounding, which has to be greater than 0 for a process to be spontaneous. Right? If a process is going to be spontaneous, that means the entropy of the universe, which is equal to the system and the surrounding. The total entropy of the system and the surrounding should be greater than 0, only then will the process be spontaneous. That means from second law of thermodynamics, I can say that if the total entropy of the system is greater than 0, then the process is spontaneous. if the total entropy of the system is less than 0, then the process is non-spontaneous, and if the total entropy of the system is equal to 0, then the process is at equilibrium. Right? So thus you could have an increase or decrease in the randomness. You could have an increase or decrease in your entropy. That is what second law of thermodynamic states, depending upon what is your change in entropy. Now, here again we have a problem. We are not interested in the entropy of the surrounding. We are only interested in the entropy of the system. Right? I can say from second law of thermodynamics, second law of thermodynamics, entropy change must be positive. Entropy change must be positive for spontaneous process. For a spontaneous process, entropy change must be positive. Right? Now, entropy change of the system and entropy change of the surrounding have to be determined, must be determined to find the total entropy change of the system. Right? But we are not interested, as a chemist, I'm not interested, I'm only interested in the system but not in the surrounding. Therefore, what we have done is we have come up with a method to conveniently express the total entropy of the system without measuring the entropy of the surrounding. Right? However, chemists are interested only in the entropy of the system. Are interested in the system and not the surrounding. As a chemist, you are only interested in the entropy change of the system, right? And therefore we've come up with a new unit, like how we came up with a unit called as entropy to measure the randomness. We've come up with another unit. I can say therefore they express the criteria of spontaneity They express the criteria of spontaneity of a process in terms of thermodynamic function called Gibbs function or Gibbs energy. So now my entropy reaction is going to be, what is Gibbs energy? I can say that Gibbs energy is defined as Gibbs energy is, you understand why I needed a Gibbs energy? Because I was not interested in the entropy change of the surrounding. I didn't want to measure that. Therefore they came up with another unit which is called as Gibbs energy. Gibbs energy is defined as G is equal to H minus Ts, where H is the enthalpy of the system that is the total amount of heat energy at constant pressure, and S is the entropy of the system.
What does P stand?
Temperature, right? Therefore, I could say that if this is how the chemists have defined Gibbs energy, then I can therefore say that the change in Gibbs energy should be equal to the change in enthalpy minus T remains constant, the change in entropy. Right? Now, since H, T and S, all three are state functions, enthalpy, temperature and entropy, all three are state functions, therefore Gibbs energy is also a state function. G is a state function as delta H, T and delta S are state functions. So do you understand why we have Gibbs energy and what is Gibbs energy? So let's now talk about Gibbs energy. So do we understand why we had to come up with another thermodynamic unit called as Gibbs energy? So let's talk about Gibbs energy now. Fifth. Gibbs energy and spontaneity. Now, we had already found out, you can say that as the total entropy is nothing but entropy of the system plus entropy of the surrounding. Right? Now, for a process to be spontaneous, we said that total has to be greater than 0. For a process to be spontaneous, change in total entropy should be greater than 0 at constant temperature and pressure. Only when the change in entropy is greater than 0, total change in entropy is greater than 0, will the reaction be spontaneous. Now let's assume that delta H is the enthalpy change in the system. We derive Gibbs energy. Let delta H be enthalpy change in system. Right? If delta H is the enthalpy change in the system, then the enthalpy change in the surrounding will be, if this is the change in the system, then enthalpy change in surrounding will be, guys, simple, minus delta H. If this is the enthalpy change in the system, in order to keep the universe constant, if delta energy can neither be created nor destroyed, right? First law of thermodynamics. If delta H is the enthalpy change in the system, then minus delta H has to be the enthalpy change in the surrounding. That means I can therefore say that the entropy change of the surrounding is nothing but entropy, yet said can be mathematically derived as the heat supplied at a particular temperature, heat supplied by the temperature. So this is going to be heat supplied is negative delta H upon temperature. So the entropy change of the surrounding now can be written as negative delta H upon T. Substitute this, so therefore I'll get total entropy change is entropy change of the system minus delta H upon T. Right? So now if I take LCM here, I will get this as T delta S total is equal to T delta S minus delta H. First I take T as a common denominator and then I take that T on the other side. So in which case I can say that multiply by minus 1 multiply by -1, minus T delta S total is minus T delta S plus delta H, right? So therefore I could rearrange this and write this as minus T delta S total is delta H minus T delta S, right? Do we get this thing here? Now this can be written as therefore what we have said, but by definition of Gibbs energy, we have defined Gibbs energy as delta G is equal to delta H minus T delta S, but by definition of Gibbs energy, thus I can say that Gibbs energy is minus T delta S total. Fine, do we get this thing here? Where we know that T is always positive, so delta G and delta S have to have opposite signs, only then can I have a negative sign here, as T is always positive, therefore delta G and delta S total should have opposite signs, only then can I have a negative reaction taking place. Thus for a spontaneous process, if thus for spontaneous process, we know that for a spontaneous process that delta S total is greater than 0. If delta S total is greater than 0, then delta G should be less than 0. Therefore, for spontaneous process, the change in Gibbs energy will be less than 0. Fine, do we get this in here? Similarly, it will be exactly the reverse for a non-spontaneous process. For non-spontaneous process, delta S total will be less than 0 and delta G will be greater than 0, and at equilibrium delta G will be equal to 0. Why? Because as delta S total is 0, therefore delta G will also be equal to 0. Fine, do we get this thing here? So thus we have now an equation which says that delta G is equal to delta H plus T delta S, which gives you the spontaneity of a reaction. Fine, do we get this in here? Now on the basis of this, you can now find out the factors that determine the spontaneity of the reaction and how they affect the spontaneity of the reaction, right? We will stop this here for the day. Thank you very much.